this is the first question. Get your code.
The camera.
Yes, if you need the first question, please raise up your hand. Tell me the one you need, we get it. We have physics, chemistry, math, biology. Read the first question, math, physics, chemistry. You raise up your hand, you get it. All the first questions are available. Math, physics, chemistry. You get it now before you go. Yes. First question. Who else for the first question? Chemistry is available. You can pick your chemistry, your maths. Pick them before your physics. Pick them before you go home. Any other question for the past questions? Maths, physics, chemistry, past questions. You did the maths question for the rest of the hand. You get it. I'll get it to you.
Please rise. On this particular topic, called circular motion or rotational motion, I want you to know that there are 4 categories of motion. The first one is what we call the kinematics, and we call it kinematics. So we're going to be doing kinematics or kinematics or circular motion. We're doing dynamics or circular motion. We're going to be doing relationship between angular motion, angular momentum, and linear momentum. So for today, we're going to be doing the kinematics of circular motion. And I said that circular motion is the movement. Circular motion is the movement of the body of mass on the same point particle. Movement of the body of mass or point particle. Movement of the body of mass or point particle around a circular path. It's a circular path. Have you written that? No. I said we're going to be treating circular motion. And I said that when I circular motion, we're going to be looking at the kinematics of circular motion. We're going to be looking at the dynamics of circular motion. We're going to be looking at the relationship between angular momentum and linear momentum. Then I said that circular motion is the movement of a body of mass, or you say point particle, through a circular path. That is the first definition, your textbook definition. But now I'm going to give you an understanding of what they are saying here so that you now get our full definition. I normally tell my students that calling it through a circular path simply means you're still talking about circular motion. So I normally tell my students to use the movement of body of mass, point particle, round the 4 quadrants we have in physics. That is, I said the movement of point particle, body of mass, round the 4 quadrants. Round the 4 quadrants. And you know that the first quadrant, the second quadrant, the third quadrant, the fourth quadrant, we treated it synonyms. Yes. So I said movement of body of mass or one particle round the 4 quadrants. Full stop. Alright. Now if I know this, I will have you to understand that what that if I'm talking about the first, second, third, and fourth, so the movement of point particles around this path. Now, what it means is that notice something. As it's moving through this path, up to this point, notice that over here is having a linear path. You see that? And when it gets to this path, it's going to get that wall. But when it's at this point, it's having a linear path. I see this. When it gets there, it has a curve. When it comes there, it has a linear path. When it gets there, it has a curve path. When it gets there, it has a linear path. When it gets there, it has a curve path. That's why we say that circular motion is that type of motion that has both the linear path and the angular path. Are you seeing it? Yes. So when we are going to be treating circular motion, before we can understand the circular motion, we have to be comparing everything we are doing with respect to what is it for the circular path, what is it for the angular path, what is it for the linear path. There are questions that will be given to you and ask you what is the linear velocity. Or what you are giving here is a motion that is given to the circular path. That's what you give them is motion. So what they are saying is, at what point do we come to this extent? Or this one, or this one, or this one. So, for example, if you are going through a circular motion and the person says, what is the tension force? You see that in that case, they are not asking you for centripetal force. So the tension force will simply be the force that goes through this angle and then it's on the angle. And how do we calculate it? We say that since it's this way, see one of the T equals to energy. And when it's this way, that is when we look at the centripetal force, which is that C will equal to N squared over R. Don't find it. And when we finish this, we now use Pythagoras to now say that the total thing T squared equals to whatever I have for this y, whatever I have for this y, T square y plus T square s. That is what they ask the potential of force. Why am I doing this? I'm trying to use this to explain what we're going to do. So that you understand that for every circular motion, you must have the linear path and the circular path. Alright. As we did with kinematics when we started with the 4 parameters that we need to know under kinematics, which is displacement. So, as we did with kinematics, we have displacement, is it not true? Velocity, and we know that displacement is essential with our distance. Then we have acceleration, is it not true? Alright, so please write down. For circular motion, we have the linear path and the circular path. In today's class, at the end of today's class, you should be able to know all those equations you see and you start grabbing it. And we have the angular path. I know I'm not too fast. Am I too fast? So I will calm down. Like I said, we have the linear path and the angular path. And what I analyze here is trying to show you that as it's moving this way, it's angular. As it's moving this way, it's linear. Then I know most of you always rush to that part of centripetal, centrifugal. If it's moving, don't worry. Let's take it gradually. Now, the first thing is going to be displacement, which is S. You know that we represent displacement with S. And we know that for kinematics, linear motion, displacement is simply equal to what? Velocity times time. Is it not true? Do you still remember? Yes. Because by the time we do V equals to S over T, then S will be equal to 0 VT. Is it not true? Yes. But here, for circular motion, we just say that this circular motion is simply going to be equal to 2 by R. If I have this to be the parts, let's say this is my circle, and I have this to be my radius, and I have this to be the parts that is covered from this X percent. This is my S. There must be an angle here, is it not true? You mean? Okay. Now this angle here, for you to be able to put together this distance, this height distance, they are telling me that it will be equal to this theta, this angle, and this. So what we call displacement in linear motion. For circular motion, we don't call it S, we call it theta.
Okay.
Are you saying it? So since we know that for kinematics, displacement is S, for circular motion, displacement is theta. So and everything about circular motion, I want you to always keep the R a constant. Just like if I ask you what is the distance of the circle, you know that the circle is 360 shading. But if I ask you the distance, say 360 and R, this 360 times R. that is the same thing with 2 pi r. Are you seeing it? That is the distance of this. So for that reason, angular motion, displacement is theta, but I will not write only theta, I will have theta r. Are you seeing it? Very important. Alright, let's now go to the velocity part. We know that velocity in linear motion is going to be s over t. Is it not true? Now, velocity in circular motion is not called velocity. It is represented with W. Hello, Constable. Constable, you want to share something, Chevy? You want to share? Okay. So, in circular motion, this velocity you see is represented with W. Now, I told you, anything in my here in linear motion, once you're talking about it in angular motion, always say that includes arrow to it. So that arrow talks about the radius, because for you to get anything, for you to be in angular movement for the radius. So this means that velocity in angular motion or the circular motion is going to be W times R. I will call this the angular velocity. Some people call this omega. So that thing in linear motion we have, in circular motion we have, and we know that it's equal to S over 2, which means that, see, I need to know that velocity is equal to omega to R. R is always a constant. But that does not mean that this is the only formula for this angular velocity. That's not the only formula. But this is simply when we are comparing, there's a difference. See, first of all, for you to enter this circular motion, you have to first of all be thinking of the linear parts and the angular parts. Then second, you now have to be thinking of when they ask you a question, they're telling you to find the angular and whatever. So what we're looking at is the relationship between the linear and the angular motion. I see it. Now, when we finish the relationship between the linear and the angular motion, we're not going to what we now call the angular motion itself. So for example, if they ask you what is the relationship between this and this is it. But if they come and ask me what is this angular velocity, what is the formula for angular velocity, I will simply use those the way we did the equations of motion. Where we said that if V is equal to S over C. So the second is that this one will be set as a because what did we say displacement is here? Should be theta. I will have theta over C. This thing means angular velocity. This is angular velocity. But if a question is given to you, they ask you find the linear velocity. Let's say they give you a circular motion question. And that circular motion question, they tell you find the linear velocity. This is not what you do. You will not use this. This is the one you use because it's an angular motion. I say it. Yes. So you have to know when they are talking about the linear parts and the angular part. That's why I started this. When we started. So what we are doing here is the linear parts. And then we are still having to know the angular part. And we said that for us to be able to know the linear part, we have to compare it with what it is in kinematics. Okay, understanding it now. You are not paying attention enough. You know why I say you're not paying attention enough? There's a level of attention you pay. The fact I even ask you, are you understanding it? You will say yes. But if maybe you are paying attention the way you want, when I now ask, are you understanding it? That's when you want to pay attention. And what you have to say is no. So you have to start from the beginning to pay attention. See what I said. When I started this, I told you that circular motion is that type of motion that has both the linear part and the angular part. Remember that it's linear motion, I'm just moving this way. Is it not true? Yes. Projectile motion, if I throw something, I'm not covering the whole quadrant. I'm just going through that. But here, if I go through this way, notice that what is taking here is an angle. And now when it comes to this one, this is horizontal. Is it not true? You go away. When it comes to this particular one, this is vertical. When it goes to this way. So for us to talk about circular motion, we have to be checking its linear part and its angular parts. And for us to be able to check the linear part, we have to derive equations for the linear part from kinematics, which is horizontal motion. So we have to be using those formulas we know for all the displacement, velocity, acceleration to derive the linear part of circular motion. Then when we finish the linear part, we now remember that circular motion also has an angular part. And those angular part, for us to derive it, we now say, okay, if this one, for example, is equal to this in kinematics, it simply means that angular velocity on this pole, we no longer be talking about whatever relationship I have by saying this one is velocity, let R, because it no longer be this way. It will not be the same way we say velocity is always displacement over time. What is the displacement? Displacement is theta, and it's always going to be vertical. So we are comparing two things in circular motion, the linear parts and the angular parts. And we cannot start solving questions if you don't understand this. You have to understand it. So that when we start solving, it will no longer be wrong. Because once you understand this thing, for the fact that we've done kinematics, you will not have issues with this again because it's the same thing. The only difference is just understanding that circular motion deals with the linear parts and angular parts. Now see, okay, in order not to confuse you, let's take it that we are still doing the linear parts. Can you hear me? Let's take it that we are still doing the linear part of the circular motion. Maybe what is confusing you is that I wrote angular part. But remember that we have to put this, so let me just use circular motion. So linear parts and then circular parts. So that you understand this now, let me use circular motion. So that you know it. So when we now get to angular part, we start using it. So this is the linear part, then this is the circular part. So we are comparing kinematics in order to get our linear part of the circular motion. I don't know whichever way I want to do it. Now see for the acceleration, hey, we know that acceleration is equal to what? Velocity over time, Shady. Now here, for this circular motion, the linear part of this is simply going to, we don't have any room, we don't have anything we call acceleration here. Rather, we represent acceleration with alpha. Are you seeing it? So we say the same. So what we say is simple. We say since V is equals to omega. Is equals to omega r. So for here, this one is the one you have to know. So this is going to be W squared. That is velocity 2 times. Then times r. Notice that everything I'm doing here, r is always constant. Yes. So r is a constant because for you to talk about circle, you must have radius. R is a constant because for you to have an arm or an angle, there must be radius there. Yes. Alright. So these are the linear parts of the. So if at any point you are solving any question in circular motion, the question can now ask you, what is the linear speed? See what they're asking you to find. They tell you what is the linear acceleration. This is what you're using. But let's say they ask you, what is the angular speed or the angular velocity? We are getting to that part. I see it now. Yes. So we are comparing the linear part, that is from kinematics. Then we are getting the linear part of the circular motion. Alright, so with that said, we've gotten S, which is displacement, Shemi. We've gotten velocity, and we've gotten what? Acceleration. Alright, please, you need to know that if this is theta r, for the fact that what we are going to be doing, I told you when we started that the unit of angle is radius, right? Is it not true? And we know that theta is for degree. Is it not true? Theta is for degree. And theta is equal to how many what in radius? 2 pi. Hope you are aware. Yes. So if that is the case, it simply means that here that I have theta r. Displacement is also the same thing. I tell you, if I come and replace this theta with 2 pi, then bring it outside. So another formula for displacement is 2 pi r. Very important. Which means that you now come to note that the linear part of the circular motion, these are the formulas you need to know for the displacement, the velocity, the acceleration. Now let's go to the angular parts. Let's go to the angular parts of the rotational axis. What? I said that for here, we know that there is velocity here, is it not true? Now I said that this particular acceleration, we have nothing to call it. There's nothing to call it here. We don't say, just like I know that velocity is W here, which is omega. Now I said we don't have anything to call it. So what we just do is that simple. Whenever we're talking about the linear part, we say that it's going to be omega 2 times. Then the r that is constant. We have nothing to call it. But you can't say this is just no. Acceleration simply, notice that acceleration for a circular motion simply does not talk about should I say change in speed. It does not just talk about change in speed. What acceleration for a circular motion talks about? Directing it towards the center. Are you seeing it? Yes. For anybody that is in circular motion, for it to maintain that circular motion, its acceleration or its change in speed will be directed towards the center. So it's no longer about increasing speed, but rather how much does it change and tend towards the center. Alright, so now that we know the linear part, let's go to the angular part. I want to claim, can I? So once we are done with this, we introduce the questions of the circular motion. Then we can look at the calculation. Then when we are done with this, we move to the next part. Remember I told you that there are 3 things we are looking at here. The kinematics of the circular motion, the dynamics, and when we talk about it, when we talk about the dynamics, it's no longer going to be force. You know that dynamics talks about respect to force, should we? But here, what we are going to be talking about is respect to torque. Because the force found in a circular motion is known as torque. While the frictional force that we'll be talking about is no longer going to be called frictional force, but centrifugal force. Are you seeing it? Yes. Alright, so for the angular part, okay, let me use this in comparison. So I will now have my angular part. So for my angular part and then the circular motion. Alright, so let's do something. When I talked about displacement, I said that displacement is equal to OR, is it not true? Right? Yes. Now, I said that velocity is equal to what? WR, right? Theta R. Alright, please, when I'm talking about this now, under circular angular pattern, what I'll be comparing is the velocity being displacement over time. I'll ask myself, what is displacement here? It's just theta, should be? Is it not true? All over. So this is the angular velocity. This is the formula for angular velocity. So if you now write it this way, another way to write it is simply, remember that this one is 2 pi r, should be? Just to remember that you see 2 pi, let's start this way. 2 pi, should be? All over C. Do you remember? Yes. So this is going to be the angular part. But if I'm comparing it with the linear part, I'm supposed to have 2 pi. Then remember that there's r here, shall we? Then there will have t. Is it not true? Yes. That is why you normally see sometimes something like this. And you need to know also that that is why sometimes when you're talking about centripetal force or centripetal acceleration, you come and see 4 pi something over r from here. Because if I know that, for example, that this square, we are coming, we are just trying to elaborate, this square over r is centripetal acceleration. Is it not true? Let's say I carry this now, this 2 pi r over t for v. So I come and see 2 pi r, then all square, and it's over t, should be? Then times 1 over r. See that by the time I square this, I have 4 pi. Is it not true? And it's going to the square, should be? Then r square over c. Then remember that it's times 1 over r. This will cancel this. So I have 4 pi square r over c. So it's not every time that centripetal acceleration is v square over r. So centripetal acceleration is also 4 pi square r over c. And we're going to get to that. But why am I doing this? So that you notice. And how did I derive that? By comparing the linear parts. Comparing the linear parts to this square. Then putting it together. But we've not gotten there. So if you don't understand, don't let's progress. So now for the acceleration, let's go to acceleration. Remember that what we are doing is the angular part, right? We are done with the linear, that is the vertical axis, so that we are checking when it curves, Remember it has to travel, that's what we are checking. So for the acceleration naturally is what? V over t, is it not true? If acceleration is V over t, we now have to ask ourselves, let's put this side to side. By doing, I have first of all that when we compare the linear part, I have W squared r, should be? Is it not true? And what was my W equals to? W was equals to what?
Velocity.
Remember that we did V equals to WR. Do you remember? Do you remember when we compare the linear parts? Is it true? So from here we can actually, okay, see what you just need to understand that in the circular part, we are adding a bit of the linear and the circular together. Yes, we are putting it together so that we now have increase yes divided by W. Or by R, so that W is the circular formula. We now have R cancel R. So W is equals to R is equal to V over R. Go to the W is equal to V over R. You see that too? So that means that I can substitute for W, V over R. Or square. I'm coming for L, then times R. So that this becomes such as V squared over R squared times R. So that if I cancel, I'm left with V squared over R. What we're trying to get is acceleration. And the acceleration here is called centripetal acceleration. Yes. So please, the idea, the concept is that when we are doing linear, we are comparing kinematics with the circular part, with the linear part. While when we are doing the angular part, we are comparing that our linear part of the motion that we derive with the circular part. So that's what we're going to get. So this is going to be acceleration. The acceleration is coming from what you have from that linear part of the circular motion. So by the time you substitute, you're able to get your answer. That's the first method to go about it. I can as well remember that S is equal to theta R, shall we? That is still on this angular part. If I make theta solid on the top here, over R, shall we? And that means it's going to be theta equal to what? Please remember I said, when we got the linear part of this circular motion, we used kinematics to compare it. Now, when we are trying to get the angular part, we are using the values, the equations we have for the linear part of that circular motion to get this one. So they are related. We can't jump from here and go back to kinematics. From kinematics, we get the linear part. But the linear part, we are able to get the angular part. So if theta is equal to S over R, you remember that W from the linear part, when we did the angular part, we said that W is equal to theta over T. Is it true? Is it true? Let's substitute for theta. Let's substitute the value of theta. Let's over R, shall we? Times 1 over 2. Is it not true?
No.
Is it true? See, now see. See over 3. Now look at theta is equal to S over R. It's still carrying the theta. So that is times 1 over 2. But see, let's do it this way. S over R will be for theta now. You don't understand, just see the elevation. This is S over R. I have divided by 2. So I can put my T here, I say times 1 over T. Is it confusing? It's not confusing. See, I have W is equal to theta over R, shall we? Theta over T. I am doing the mathematics for you. You do the mathematics. So if you are there, once you see someone that is trying to pamper you with reading the writing, you just relax. So you do it yourself. Fine for me now. Substitute S over R for theta. Then into this formula, what do you have? You will see you have that this is going to be S over R T. Is it not true? Yes. And if you look at this level, this thing looks like V. Displacement over time, you see now velocity. So that means that this is the same as saying V over R. I seen it. So whichever way you go about it, this is how you get that W is equal to V over R. Notice that we are not using, notice that everything we are doing is we are comparing the linear parts then and the circular part. So when you get this now, it simply is that if come here and now substitute, we should be able to get V squared over R. It's not hard. It's not hard.
I'm confused though.
You are confused. Don't worry. See. I want to connect. Can I connect? It's not hard, but the problem is that some of you, there's this natural tendency of refusing to understand, refusing to agree. The equality might not be understanding. Yes, so I see. I have from the angular part, we said from the angular part, velocity is velocity, but in circular motion we call it velocity of omega. I said the velocity should be equal to displacement, and this is what we have displacement in circular motion over time. See now to yes. So if we have this, we are saying, remember that when we started, we said that S is equal to theta over theta R. See now comparing the linear parts. Linear parts kinematics, you get the linear part. Linear part, you get the circular part. So, but if you let it very well, you can even be moving across without noticing. So, making theta subject of the formula here, we divide both sides by r. So that we get that theta is equal to s over r. I say this. Now, I now said, substitute the value of theta here. Is this theta? This theta is here, is the same as saying theta times 1 over t. Do you agree? Should it? So I'm now saying that put the value of theta here, which is s over r times 1 over t. And if you look at this, whether it's like something you know in kinematics, which is s over t means velocity. Is it not true? So I just write that, and this way, I will now have s over t. It's the same as saying s over t one side times 1 over r. Multiplication is distributive. So this will now give me velocity. So velocity times 1 over r, v over r. That is my W. Whichever way you want to put it. I see it. Okay. No, don't worry. Thank you. So now that I have this, I can now substitute inside that value that I compared the linear part. From the linear part, we got that acceleration is equal to W square r. So substitute inside that linear part. Remember I told you we are using linear part for the angular part. So if we look at acceleration is W square r. So just substitute this v over r for W. So that I will now have okay. So I will now have I said from here we'll come from that linear part to know that x equals W square r. So if we substitute for W is v over r all square then times r. This is going to be the same as saying v square over r square times r. This can cancel this square. So that I'm left with v square over r. I say this. It's not hard. It's not hard. The only thing that will help you is always remembering that circular motion and kinematics, they are not different. But just that for kinematics, you'll be able to compare it with the circular part, circular motion to get the linear part. And to get the linear part is simply adding r to everything. While for the circular part, it's simply the same thing you have for each one. Just the one that has over t, you carry over t, you carry over t. Then you are now substituting. So with this, let's move to the equations of a circular motion. I want to claim. I know it's not hard. What you just need to do is to take time and think about it. But it's not hard. So equations of a circular motion. I know we've got kinematics. So we don't need to start from the beginning to learn what it is. And I call master talking. What did he tell you? Okay, so please write equations of a circular motion. Can I explain? So please, have it in mind. Have it in mind, before the equations of the circular motion, let me just throw a little light on what we call tangential acceleration. You know, I normally start my class with giving the formulas and explaining. It's because some people are fond of once they enter your class, if you are solving questions, let them copy questions, solve. They don't even know where they are going. They just start with formulas. And when the question do one kind, you see that you are no longer there. That's why we normally start our class with deriving the formulas and how they go about it. Now, please, whenever they tell you centripetal acceleration, that is the acceleration that, should I say, that gives you everything called circular motion. For a body to rotate, you say it is the acceleration that pulls a body towards the center of the earth, or you say towards the center of rotation, or towards the fixed part. Once that centripetal acceleration is not there, that body will just start moving slowly. So, if for example, I have a body going this way, let's say this is the velocity, and I have a force applied to this body, F. You see that if there is no force, if this force is not fixed, and this body tries to move this way, it will go straight, shall it? Or if this body is fixed, if there's a force here, this thing is nailed. If you want to move here, because it's fixed, they need to rotate. You see how to? Yes. So this force here is what we call centripetal force. And the acceleration here that will be possible, that will be that MA, is going to be the centripetal acceleration. I see, just like for example, if you carry something, you are doing it like this, doing it like this. Normally, when you start it, your hand is not paining you, Shemi. Or if you say you would stand, your hand will start paining you. You know, yes, reason is because there's the force that wants you to stop doing that thing. That's the force that tends to pull that body away from that center. We call that force centrifugal force. So you can notice the frictional force found in circular motion is known as centrifugal force. So you say center pull. While the force pulling the body to the center of action or center of rotation is called centrifugal force. Or you say, and the acceleration is centrifugal acceleration. So I said the frictional force found in circular motion is called centrifugal force. Or you call it center free. I said centrifugal. I can never say centripetal. I said the frictional force found in circular motion is known as centrifugal force. Never will I say centripetal. Centrifugal. In fact, how I normally tell my students to remember it is that this F stands for friction. This F stands for friction. Why for centripetal? You know that this part will be shaping. That P stands for center pointing. Okay. Please, if you've not paid for tutorial or you just joined, you wish to pay, because I know some persons meant me earlier that this one. So please, she's around. She will go around. You have your tutorial fee. You give her. Yes. If possible, collect account numbers. So whenever I see this, I know the center formula. It says center friction. Why center point? Alright, so with that said, another thing I want us to notice, for example, see, I don't know what to do it with, but notice that if I'm rotating this now, if I'm slow, you are able to notice something. In what direction am I going? Towards the right, this way. And if I'm going this way, you're able to notice that I'm going this way, towards the left. Is it not? Yes. But notice that if I'm too fast, just like if your fan is rotating, you don't even know which direction the thing is going. Is it not true? Yes. Now that observation you see with your eyes is what we call tangential acceleration. So it is the acceleration that is found in a body moving in circular motion when the body is slowing or moving fast. When the body is slowing down or moving fast or speeding up, the acceleration here is what we call tangential acceleration. Why? Because you're able to now notice that yes, as it's going towards this direction, it's going towards this direction. And notice that as that thing is happening, it's more like, is it not true? Yes. So you have a 90 degrees path, you have a path that is going this way, or a 90 degree path and a path that is going this way. That is why we normally give this as tangential acceleration is equals to acceleration times the radius. So whatever acceleration you have times the radius. And that radius we are talking about is simply if it's going this way. That's as if it's going this way or going this way. Whatever acceleration you have, then the radius is that particular line, straight line you are noticing. Notice that it is cutting through a point and there's a straight line in between. So that's what we call tangential acceleration. You need to know that. So we have centripetal acceleration. And you need to know that this centripetal acceleration is not peculiar to anything. It's not like maybe there's a particular acceleration that causes centripetal. No. It is anything that causes a body moving in circular path to maintain the center. That's what we call centripetal acceleration. Why, if you notice the body is slowing down or moving forward, the type of acceleration found there at that point is what we call tangential acceleration. Very important. Alright, with that said, we need to point to what we call equations of the circular motion. Equations of the circular motion. And under these equations of the circular motion, it's just the same thing with kinematics, or equations of a straight line, or equations of a linear motion. Or you say horizontal motion, or you say motion in one dimension. Never when you call this, that's kinematics. So we know that in kinematics, we got that S first of all is equals to ut plus half a squared capital. We know that we also got that V is equals to U plus A capital. And you know how we derive this equation? Yes, we derive this. So if you're not in class when we started class, like I normally say, don't panic, because we are going to be doing by A by B class. We are supposed to start that class this week, but after discussion with the tutors, all of us agree that it's best to start in January. So that January, you can just start everything from the beginning. That a good number of persons will eat rice and chicken. Forget their notes. So by January, we'll be starting from the beginning. So for people that are here, or that are here now, by that time, it will be revision to them. So by January, we'll be starting from the beginning. So then I said that to relate the equation, we only use S equals to U plus V over 2. And what is this? This thing that we're seeing here, what is good value to when we learn this? Average velocity. Yes, I see. This is the equation you normally use to write anything on equations of a straight line. So when we start this, if we want to derive, we can derive. But we just want to easily compare the two. So now that V squared is equal to U squared plus 2AX. Is it not good? So for me to derive this, because that of the equations of the circular motion, all I just need to do is remember that S is called theta. Is it not good? Please try and S is called theta. And what I call U, velocity, is called W in circular motion. But the only difference is that for linear kinematics, we call it V, final velocity is V, and initial velocity is U. But for circular motion, final velocity is just W, while initial velocity is W. No. I think yes, you have to use what is generally accepted, so you don't go and make mistakes. So if that's the case, I'll just replace it. So W naught plus half this day, I replace it with something that is like half or the day or the nobody complains about that one. Why for this I have W? So the name was W naught plus so I now have this one to be W squared equals to W naught squared plus 2A. What did I write here? 2A. So I'm here. Yes. So 2A. So please, this is the equation of the circular motion. So it's the same thing with kinematics. Just that you have to now note that there are certain things that will change. So please, when you get home today, try to think, and when I post the video, try to memorize everything you find here. So that when you are given any question, it will be difficult for you. So there you have it. Another thing I want to mention before we start solving the calculation is this. Okay. You were just pressing your phone, then you wake up. You want to ask. I noticed it. I said, that's it. I said, if you want to leave it as said, you can leave it. You want to keep it at that point. But nobody complains for the acceleration. Yes, nobody complains for the acceleration. So if I know this now, see, another thing I want you to know is, for example, please pay attention. Do you know that if I say V is equal to change in displacement over change in time, I want you to know this. Do you know that what this change is differentiation? Are you aware? Differentiating displacement and differentiating time, you get velocity. I see it. Now, notice something. If I choose to cross multiply here, this one will go here, shading, which means that I have V, C is equal to S. Shading? Now, if I want to make S displacement subject of the formula, when differentiation cross equality sign, it becomes what? Integration. You see that? So S will be equal to integral of V with respect to time. Why am I saying this? It's important to notice anything like this. All those formulas you normally see us do, where they tell you change in this over change in this. Have it in mind that if we are not doing changing, if we do the other way, that what we have is integration, because we are going to be making good use of it in this particular course. Especially when we start getting to talk angular momentum. We are going to make use of it. So notice that all those formulas will normally give you, but sometimes they don't even mention the change part. Notice that for anything over something that is normally a changing, that is differentiation. And if I choose to make the other one or any of his subject of the formula, it simply means that it's going to be integrating what is on the other side. just like we've done here. So note it. This is a symbol for inspiration. So this one is S. So note it because it will be useful. Alright, with that said, let's go to that our PDF. I want to bring this. Copy. Please go to the PDF I posted, the first one. Solve question 1 and 2 here for me. Solve question 1 and question 2. You go camera. Don't fall my camera down. Because you know I normally make sure I video a class. Because the way people ask me questions these days is getting to. I will not even come to school. Then these two people, physics department. They don't even wait for you to come to school. They have to go physics question and come. So I like once you are teaching or having class, you are videoing it. So that once you come, I tell you, go and see the video. I open it and show you, you watch it. So that you will not, be stressing. So please check the PDF. The first PDF, question 1 and 2, solve it. I'll go around and check them. We'll do it together. Check the WhatsApp group. Check the WhatsApp group. No, check the 2 questions I posted on circular motion. The first one on that general group. This one is the second one. The first one, go up. So how can you be asking me when? Go up and check it. It's in the group. Are you new to the group? No, the first one, not this one. This is the second one. So guys, check.